Okay, I wanted to finish this module by looking at an example, an additional example that you may or may not pay attention to, um, about induction. The reason why I didn't include it, this should be meant as an extra, um, and the reason why I didn't include it in the main part of the lectures this week is because it's a statement about real numbers. And since we haven't proved the existence of real numbers yet, and it should be kind of a separate thing, just to prepare yourself for proofs by induction, where we are allowed to use real numbers. Okay, so this is kind of an example that you should set up, uh, set apart in your mind. So again, this is induction. Uh, Induction, and you see why I kind of left it apart. The the existence the existence of the real numbers. Real numbers. We haven't shown that these so-called real numbers exist yet, so we haven't constructed them. Um, in the book, what happens is they start by characterizing and defining axiom, the axiom of completeness, which is missing for the rational numbers, and they say the real numbers is satisfying that. I mean, set with the same properties as Q. I mean, field order set, um, but which in addition satisfies the this completeness axiom. The only thing here to pay attention is that while you can introduce it as an axiom, you need a model. You need to show that an object satisfying all those restrictions actually exists. And that's the point of the final part of the book. And in fact, we'll just take a small detour next week to show that these real numbers actually have a model. Okay, so we can from then on assume that we're talking about the same thing when we talk about real numbers. Okay, but for now, so the point of this example is just to give you one more application of the principle of induction. But now, I mean, for just for the time being, we're going to assume that the real numbers exist. So what is the problem? So we define the sequence x of n in n, recursively as follows. X1 is going to be set to be equal to square root 3, and assuming we have defined the nth term of the sequence, then the next term will be equal to the square root of 3 plus x of n. We are asked to show that this sequence is non-decreasing. Okay, so the point is the same as in the previous example. That one was perhaps not so interesting in the sense that it was linear function, or a fine linear function of xn, what defined xn plus 1. Here we have to deal with a nonlinearity, so the square root. So that makes it more interesting from the point of view of applying the induction principle. However, we already know that when taking the square root, I mean, we may not, even if we have, we're taking the square root of rational numbers, we may end up with things that are not rational numbers. And since we don't know that there are such things as real numbers yet, we're not allowed to write this here. This doesn't make sense unless we, for rational numbers, unless yeah, no, this doesn't make sense for rational numbers, and it only makes sense when we assume the existence of real numbers. And this is going to be an exercise that I'm going to leave for you, but in the same way as you saw in section 1.1, that the square root 2 was not a rational number, you can prove in the same way that not even the first term is not a rational number. Okay, and this expression, you may think that it may or may not contain, some cancellations that even though when the xn may not be a rational number, maybe take the square root and add 3, you may end up with a rational number, but that's not the case. But we will not get into that because it's not really relevant. The important thing here is that the sequence we're defining here makes sense only if we're talking about real numbers. Okay, but we can, assuming that, we can give an extra application of induction principle, and which is the point here. And this is actually something that we're going to be doing very often. Dealing with expressions like this. So that's why it's more interesting than other artificial examples. And so how do we proceed here? Remember that we need to prove 2 things. We need to prove that it is true the sequence is non-decreasing in the case when n is equal to 1. So that is x1 is less than or equal to x2. And then the case n implies the case n plus 1. Or xn is less than or equal to xn plus 1. Okay, we prove, we start with the case n equals 1. We need to show that square root 3, which is equal to x1, is less than or equal to x2. But the square root of 3, the square root being an increasing function, is definitely going to be less than the square root of 3 plus the square root of 3. This is a positive number. And we are adding a positive number to 3, so that means that what's inside the square root is certainly greater than or equal to 3. and this in turn is equal to x2, and this proves the case n equals 1. Now for the case n plus 1, assuming the case n, we again do the same thing. So we want to show that x sub n is less than or equal to x sub n plus 1, and x sub n is equal to the square root of 3 plus x sub n minus 1. Remember that here we can assume that n has to be greater than or equal to 2. We already proved the case n equals 1. And so this is certainly less than or equal to the square root of 3 plus xn, which is equal to xn plus 1. And why do we have this inequality here? Because xn minus 1 is less than or equal to xn. So, okay, so in fact, I just made a small mistake, and small imprecision in labeling my thing. So, in fact, what I wanted to show is that x of n plus 1 it was less than or equal to x of n plus 2. And so here I need to add plus 1 here and get an xn here. So, everything that's said here is actually correct. It's just a matter of labeling things correctly. So I'm assuming this. This is what I'm assuming when we assume the case n. xn is less than or equal to x sub n plus 1. And so the conclusion here is that x sub n plus 1 is less than or equal to x sub n plus 2. So we approve what we wanted. Okay, there are many things that I wanted to mention about this example. So one thing is that we've shown that this is an increasing sequence. This is kind of a side note, so observation. We can also show that xn is bounded from above. So this means there is a constant c greater than 0 such that xn is less than or equal to c for all n in n. The way we'll construct the real numbers will then guarantee that there is a real number x such that xn tends to x as n goes to infinity. We'll make, I know that you're familiar with the notation already from calculus courses, but we'll make rigorous we'll perform a rigorous treatment of this. So basically everything that we kind of hand wave in the calculus theory sequence, when we said something converges something, will be treated very rigorously here with epsilon deltas. So here, this is what we mean by that. So epsilon delta treatment. Okay, so then so the two key things here are that x sub n is increasing one for one, and the second one is that xn is bounded from above. And something that we'll refer to as the least upper bound property, or the axiom of supremum, will allow us to conclude the existence of such limit x. Okay, limit, again, we have to forget for now what a limit is. You have to forget what you've learned before. We'll treat this very rigorously, but there's going to be such a number x. You still have, well, you still have the kind of the intuitive notion of what that means. And so this is just notation. If you go back to the way xn was defined, we define x1 to be equal to the square root of 3 and x sub n plus 1 as the square root of 3 plus xn. Okay, so if we iterate this, we get that x should be equal, which is the limit of this expression, is equal to the square root of 3. This is just, some x sub n plus the square root of 3, etc. Which is an expression that you may be familiar with from Calc 1 or from some recreational math books. So this is just a notation, but people, may have asked you to find the value of this expression here on the right. But now we can actually give a sense, make sense of these expressions here on the right by using rigorous analysis. And that's what will come next when we delve into the construction of the real numbers next week in the next module.